Okay, so right away I take a look at this and I want to think about whether my parabola is opening like up down or side to side. So which direction will this parabola be opening?
Is that up, down?
So because the y is squared, that's not the one that we've usually been doing, right? We've graphed parabolas for a long time, but it's always x squared. And the ones that we've been doing for a long time open up and down. So when it's x squared, it opens up or down. So when it's y squared, it's going to be opening side to side. And we're not sure whether it's left or right until we establish whether our p-value is positive or negative. So this is one that is going to involve completing the square for the first time. Right, we're all multiplied out. So we'll start by getting organized. We'll get our, we know that we're going to have to complete the square for the y because that's the only one that has a quadratic term. So we'll get our y terms on one side and then everything else on the other side. If the leading coefficient of y squared there is anything other than 1, we'd have to divide through by it, but it is 1, so we can just go ahead and complete the square. 8 divided by 2 squared. We're going to add 16 to both sides. It's going to give us a y plus 4 quantity squared on the left and 8x plus 24 on the right. If you look back to our standard form here of a parabola, you'll notice that inside the parentheses where you have the x or the y, it always has a coefficient of 1. So to get our equation that we've just completed the square for in our standard form, whatever the coefficient is over here, factor it out. Now, it usually is a whole number. It's something nice, but I guess it could be a fraction. I don't intend on doing that to you, but it could be. So we need to make sure to factor that whole thing out. So that's y plus 4 squared equals 8 times x plus 3. And we're in our standard form of a parabola. We know that this out here is 4p. So that means that p is going to be equal to positive 2. Since p is equal to positive 2, that tells us that our parabola is going to be opening to the right. Questions on anything so far? All right, well, let's identify our vertex, start graphing this. Where is our vertex going to be located?
-4, -3.
Everybody agree? -4, -3? Well, be super careful. This is a really common mistake, and I've made it plenty of times myself. Remember that the H is always with X and the K is always with Y. So you can't just go like left to right order. So this is actually going to be -3 and -4. So I'm going to plot it here, -3, -4. Oh, hold on one second. Here, buddy, look, Elliot's on. You could go in the other room and talk to Elliot if you wanted. All right, Heather, can you help him unmute and start the video over there? Do you know how to do that? Be careful with my computer. It's one thing letting them use their tablets to video chat, but when I give them my computer, I have to hold my breath. Okay. Well, we've established that our parabola is going to be opening this way. Again, that's not a good drawing. That's a bad drawing. I just like to kind of give myself that guideline so I make sure that I get my directrix and my focus the correct place. Remember that our directrix and our focus are each p units away from our vertex. The directrix is behind the parabola while the focus is inside the parabola. So that means that our directrix is going to be 2 units behind it right here. And our focus is going to be located p units, 2 units inside the parabola from my vertex. So it's going to be right here. And then lastly, we need to figure out how wide this parabola actually is. Our full width, our latus rectum is 4p. So from our focus, I'm going to go 2p up and 2p down. Those will give me the points on my parabola. So we're going 4 units up and 4 units down. And we draw in our parabola. Questions on our graph? We just need to label our focus and our directrix. Our focus is the ordered pair. What do we got there? -1, -4. And our directrix is a vertical line, so that's going to be x equals -5. Questions at all on graphing parabolas?
Yeah, how do you find the directrix? Like, how do you know what that is?
It is p units behind the focus, behind the vertex of the parabola.
Oh, so once you have P, you just
Yep,
you go backwards?
you got it.
Okay.
Well, it depends. If it's facing to the left, then it would be to the right. So
Also, it's just behind it. Like,
it's just behind it. So this here is p units. This here is p units.
I gotcha.
That's 2p. This is 2p.
All right. That's cool.
Anybody else? All right, we got several application problems here. The reflector of a flashlight is in the shape of a parabolic surface. The casting has a diameter of 8 inches and a depth of 1 inch. How far from the vertex should the light bulb be placed? Oh, anything like the light bulb in a flashlight, the little thing that sticks out of your satellite dish, anything like that where you're working with a parabolic surface. This thing in the middle that they're talking about, this focus light or focused signal, this should always be located at the focus. So basically, they've given us this information and they're asking us to find the focus of this parabola. But in order to identify the focus, we need to know the p-value. So we basically have to write the equation. All right, so I'm going to start with the diagram. And just like with our elliptical application problems, I try to get things, with the ellipse, we tried to have the major axis coincide with the x-axis. So here with my parabola, I try to get my vertex to line up with the origin. And I could be holding the flashlight vertically or horizontally. So I usually position it vertically just because I'm more comfortable with a vertical parabola because I've been doing it for so much longer. All right, so the reflector of a flashlight, parabolic, the casting has a diameter of 8 inches and a depth of 1 inch. So if I'm going to put the vertex right here on the origin, and the diameter is 8, I'm going to go 4 in either direction. And then up 1. So it looks something like that. So we have the point -4, 1 and the point 4, 1, and this here is our vertex equal to the origin. Any questions on anything I've done so far? All right, so this is a vertical parabola. That means that we're going to be using the equation x minus h squared equals 4p times y minus k. And I know my hk because we've put the vertex at the origin. So this becomes x squared equals 4py. And we're looking for the focus. We know the focus is p units away from the origin. So basically we're looking for p. We're going to take one of these ordered pairs, doesn't matter which one. I'd be inclined to take 4, 1 because it has all positives. And we're going to plug that in for x and y into our equation over here, and then we can solve for p. That'll be 4 squared equals 4p times 1. 16 equals 4p. So p equals 4. We know that our focus is p units away. And the light bulb should be placed at the focus. So how far from the vertex should the light bulb be placed? 4 inches. Questions at all? All right, let's try another one then. Here, the cables of a suspension bridge are in the shape of a parabola. The towers supporting the cables are 400 feet apart and 100 feet high. If the cables are at a height of 10 feet midway between the towers, what is the height of the cable at a point 50 feet from the center of the bridge? Round your answer to the nearest hundredth. So I'm definitely going to start with a picture. So it's a suspension bridge with these 100-foot high supporting towers. And these are 400 feet apart. These are 100 high. And the cables are at a height of 10 feet midway between. So, all right, I'm going to throw in a y-axis to be the middle. And I would coincide the x-axis with the bottom of the bridge here. It says that the cable is 10 feet up, midway between. So I would put the vertex right here. So the vertex isn't quite on the origin, but I think it's going to help us when we're writing the equation. So here are our cables. Oh, I have my vertex here at the point 0, 10, and then I have these other 2 points here and here. We know that the distance between those two towers is 400, so we're splitting it. This will be the point -200, 100, since our towers are a height of 100, and this one's going to be 200, 100. Any questions on the diagram? The question ultimately is, what's the height of the cable at a point 50 feet from the center of the bridge? And we could go left or right because we know these parabolas are symmetric. I'd probably go to the right just because it'd be positive numbers. But in order to answer that question, we have to have the full equation of the parabola. All right, well, it's a vertical parabola, so we'll be using the equation x minus h squared equals 4p times y minus k. We know our vertex 0, 10, so we'll plug that in. This will give us x squared equals 4p times y minus 10. The only thing we need to have like our full equation is our p-value. So we're going to do the exact same thing we did in the previous example to get our p-value. We're going to just take one of our points. Again, I'd choose the one with all the positives. And we're going to plug it in and solve for p. Any questions so far? That's going to be 40,000 equals, let's see what we got here. There's 90 in the parentheses times 4, 360p. The p is going to be 40,000 divided by 360. And that simplifies, but that doesn't like go down to a nice integer or anything. This is going to simplify to p equals 1,000 over 9. And we want to keep it that way. All right, well, now I can take this I can now take this p-value and plug it into here, and we'll have our equation. So x squared equals 4 times p times this y minus 10, and then I just clean that up a little bit. So we're looking at 4,000 over 9 times y minus 10. But that's not our answer, right? This is just the equation that we're going to use to find our answer. So the question is, what is the height of the cable at a point 50 feet from the center? So they're asking us to find the height, which is a y value, when we're 50 feet from the center. So the 50 feet is an x value. We're going to plug 50 in for x and then solve for y. So that'll be 50 squared equals 4,000 over 9 times y minus 10. That's 2,500 equals 4,000 over 9 times y minus 10. Dividing both sides by 4,009, it actually, believe it or not, turns out to be a relatively decent number. That I multiplied by the reciprocal, and you actually get 5.625, which is crazy that we get something decent. And then that's going to be equal to y minus 10. So the last thing we need to do, add 10 to both sides. We get y to be equal to 15.625. And our unit is feet. Questions? So I really like the application problems for the conics because, I mean, they're applicable. There's a lot of conic sections. You start looking around, you'll see conic sections all over. So I really like these kinds of questions for the test. And especially then I don't have to deal with like graphing in my math lab and things like that. So I would definitely be prepared for multiple application problems on that next exam for conics. Anybody, questions on this one before we do the last one? Okay, last one. A bridge is built in the shape of a parabolic arch. The bridge has a span of 120 feet and a maximum height of 25 feet. Find the height of the arch at distances of 10 and 50 feet from the center. We'll round our answer to the nearest hundredth. So I've got this parabolic bridge. So here we have a vertical parabola, but facing down. We have two options. We can either, well, I would definitely put my y-axis going through the vertex. And we have two options. We could either put the horizontal one here and then have like negative points down here. But personally, I'd probably be inclined to put the x-axis here and then just have a vertex that's been then moved up. All right, so a bridge, it has a span of 120 feet, so we'll split it 60 and 60. So that's going to make this ordered pair negative 60, 0, and this one over here positive 60, 0. And it has a maximum height of 25 feet, so our vertex is going to be 0, 25. So if we had done it the other way, where we had put the x-axis in line with the vertex, we would just have a vertex of the origin, and then our points would have been negative 60, negative 25, and positive 60, negative 25. We'll still get the right answer, the same answer in the end. But I'd rather have some more zeros in here instead of all those other order pairs. Okay, vertical parabola pointing down, we're going to use x minus h squared equals 4p times y minus k. And since we're pointing down, I anticipate that my p-value is going to be negative. So let's plug in what we know. First, I'm going to plug in my vertex. Oh, our equation simplifies to x squared equals 4p times y minus 25. And now it's time to find p. This is just like the last one we did with the suspension bridge, where To answer our question, we need our full equation. So we need to figure out our p-value. We'll find our p-value by plugging in one of these other ordered pairs. And then once we have our equation, we'll plug numbers in to answer the question. As always, I'm going to choose the one with all the positives. So that's 60 squared equals 4 times p times 0 minus 25. 3,600 equals, it's going to be negative 100p. And again, when we solve for p, oh no, we do get a nice number this time. Dividing both sides by negative 100, we get p to be negative 36. Questions so far? So we get that negative p-value like we anticipated. To get our equation, we're just taking this number and we're plugging it in here for p, and we'll have our equation for this parabola. That's going to be x squared equals 4 times negative 36 times y minus 25. We'll clean that up a little bit. X squared equals negative 144 times y minus 25. So there's the equation of our parabola that we're going to use to answer these questions. Any questions on getting the equation? All right, well, the first question says find the height of the arch at distances of 10, and then we'll do it again for a distance of 50 feet from the center. Well, they're asking us to find the height, which is the y value, at a distance of 10 and 50 feet from the center. So we're looking at plugging in, we have two little problems to do here. We're plugging in an x value of 10 feet, and then we're going to plug in an x value of 50 feet and find the corresponding y values. So I anticipate, I know there's no proof by picture, but looking at my diagram, I anticipate that my answer when plugging in 10 is going to be relatively close to 25, whereas my answer when I plug in 50 is going to be way less, much closer to 0. Okay, so let's plug in just two little problems. All right, so plugging in 10, that's going to be 10 squared equals negative 144 times y minus 25. 100 equals negative 144y. Oh, you know what? It'd probably be easier to divide by that negative 144 instead of distributing. I'm going to do that instead. All right, so dividing by 144 doesn't go in even, but I can simplify the fraction. Negative 25 over 36. So it follows then that y equals 25 minus 25 over 36. And then let's just plug that into our calculator. Anybody get an answer? And we're rounding to the nearest hundredth. Anybody answer? 25 minus 25, 36?
I got 24.31.
Anybody else get that? That sounds about right to me because, 25 over 36 is less than 1.
Yeah, if my calculator didn't spit out freaking fractions all the time, that'd be amazing.
Oh,
I
that's
got-
Do you
super
have a
easy.
fraction do you have a fraction to decimal button? Mine does, and it'll just make it a real number.
I'd have to imagine mine does, but I just don't know where it is on this crazy.
I know exactly. Here, let me help you real quick. Let me fix your calculator.
All
I'm
right.
gonna stop sharing. I need to put your calculator up.
Okay. Hold on.
What the hell do I need to
How?
do?
I don't know if
Oh,
you can even
God.
see that.
Okay, stay right after
gonna be
class.
hard.
I'll help you. You just got to change a mode. You're in math mode. I can't. You're like this tiny little box
Oh,
on my
okay, wait.
screen. So I don't know how
Okay.
to blow you up and make you big.
All right.
Yeah, I'll fix that right after class. Super easy.
Oh wait, I might be able to do it here. I don't know. All right, just keep going. I'll
Right
work on
after
this
class.
one.
Don't worry about it. I'll fix it.
Okay.
All right, so now we're going to do the exact same thing, but this time we're plugging in 50 for x. So why don't you guys do it? I'll pause my recording here. Okay, sounds like everybody 7 point. Oh, wait, you said what? 7.38?
7.638.
Oh, okay. All right, so we're going to go to 6.4 on that because we're rounding to the nearest hundredth. Okay, great. That's parabolas. Anybody questions at all on parabolas? Okay. The last topic in this whole chapter, we're already almost done with chapter 9, is parametric equations. And this is the exact same thing that we saw in trig. So consider throwing a ball at each different time. The ball is located at a different position. It has a different x and y coordinate. Furthermore, the action of throwing a ball has a vertical and horizontal effect on the ball. We can graph this event telling where the ball is located and when the ball is at a given point on its path. The variable t is called the parameter, and it gives the various times for the ball's location. The equations that describe where the ball is located express both x and y as functions of t and are called parametric equations. The graph of parametric equations is called a plane curve. So suppose that t is a number on the interval I. A plane curve is a set of all ordered pairs x, y, where x is equal to f of t and y is equal to g of t for t in that interval I. So basically that just means that we're plugging t into some function f to figure out what x is, and we're plugging t into another function, call it g, to figure out what the y value is. So when graphing a plane curve, we're just going to select some t values on the given interval. We always, if it's an abrupt starting point, you always want your first t value to be there. I mean, just like you would an XY chart. And what we're creating is a TXY chart. So for each value t, we're going to use the parametric equation to compute an x and y value, and then we'll plot those points, x, y, in the order of increasing t and connect them with a smooth curve. When graphing parametric equations, we want to indicate the orientation, or like the flight path. We're going to do that by including arrows on the curve from increasing values of t to indicate the flight path. Don't make this hard. So we want to graph x equals t minus 1 and y equals t squared, where t is in between -2 and +2. We're going to make a t xy chart. So we just have a third column. Now, t only goes between -2 and +2. That's not very many numbers, so I'd probably pick t for every one of those numbers. We frequently use 5 points to graph. And then we'll plug in. Personally, I usually like to do the whole x column and then the whole y column, but of course it doesn't matter. I'm going to do all the x's. For x, I'm just taking t and minusing 1. And then for y, I'm squaring my t values. And then we have our 5 ordered pairs to plot. Questions at all on getting the ordered pairs? All right, well, let's plot our points then. Once we have them plotted, we want to connect them in increasing t. And then I'm going to make sure to go ahead and put my orientation arrows in there as well to indicate how t increases. And there we go, that's it. Notice that this parabolic shape abruptly starts and stops. Make sure you're not putting arrows on the end. Questions, anybody? All right, let's try another one. This time, x equals t plus 1, while y equals the square root of t, and we want to choose t values greater than or equal to 0. We're going to make our txy chart. So our t starts at a specific number, but does not stop at a specific number. So I'm definitely going to start with t equals 0, but then I can kind of choose whatever I want bigger than 0. I want to choose numbers that are going to make my life easier. I noticed that y is defined to be the square root of t. I don't feel like plotting a bunch of decimals, so when I see that, I would be inclined to choose t values that are perfect squares, so when I square root them, I get nice numbers. So I'm going to choose 1, 4, and 9. You certainly don't have to. You can do decimals if you like. Now we'll plug in and get our corresponding x and y values. For x, it's just t plus 1, so we get 1, 2, 5, 10. And then for y, we're taking the square root of t, 0, 1, 2, 3. We have our points, we're ready to plot. We'll connect our dots in increasing t, so we're starting here at 0. And here our graph does not stop, so it does get an arrow on the end, and then be sure to go back and put your orientation arrows in as well. There we go. Questions at all on graphing parametric equations? Next, we're going to talk about how to convert from parametric to rectangular. This is also called eliminating the parameter. We're going to solve one of the equations for t. I usually try to solve the x equation if I can for t, unless it's like super horrific. But usually we like our functions to be y equals something, not x equals something. So I typically try to solve the x equation for t. Then we're going to substitute the expression that we've gotten for t into the other parametric equation, and that should be it. So it'll be easy to solve this one for t. Right, we're going to get that t is equal to x plus 1. And then all we got to do now is take this and plug it in here and clean it up. We end up with y equals x plus 1 squared. We can easily, if you're asked to find the domain, you can easily find the domain if you've solved the x equation for t. So to find the domain, right now we have it defined that t is in between -2 and +2, but we've also established that t is equal to x plus 1, and we need the x equation solved for t to be able to do this, because domain is x values, not the y value. So I'm going to substitute that x plus 1 in for this t over here and then solve for x, and that'll give us the domain in rectangular. Subtracting 1 from all sides, we get x to be in between -3 and 1. So if you are asked for the domain, we can find it that way. Questions, anybody? Okay, let's convert x equals the square root of t and y equals t minus 1, where t is greater than or equal to 0. Let's convert that into rectangular. Okay, so we're going to solve one of the equations for t. We'll try to do the x one. It's not so bad. We can just square both sides. And we get t equals x squared. So now we're going to take this x squared and plug it into our other equation for t. That's going to give us the rectangular equation, y equals x squared minus 1. So I want to talk about the domain here. And this is kind of where I feel like domain for parametric equations sometimes is tricky, because we got to do it a lot of different ways depending on what type of problem we have. See, I can't do the same thing for domain this time that I did last time, because if I take just that x squared and substitute it in for here, I get x squared is greater than or equal to 0, and that happens all the time. Right? If we just graph this, we can see it's always 0 or greater. But this is not correct. You see, the parametric equation has x defined to be the square root of t. The square root of t is never going to spit out anything other, is never going to spit out a negative number. So that means that the square root of t has to be greater than or equal to 0, which means that x has to be greater than or equal to 0. Therefore, the domain here would be 0 to infinity. So I feel like we have to use a little bit more intuition with finding domain here. It's not always just, oh, just plug it in and then that's super easy. I can't do the same thing every time. Questions at all? Does that domain make sense? All right. Let's convert x equals cosine t, y equals sine t, where t is in between 0 and 2 pi, into rectangular. Well, anytime we're given a parametric where x and y are defined as trig functions, we do the same move. So we got two of them here back to back, and we're basically going to do the same move for both of them. You'll notice the second one has extra stuff other than just the sine and cosine. But I'm just trying to be general for all the trig ones. So for any of the trig ones, what you want to do is isolate sine and cosine for both equations. So here it's already done for us, so that's pretty easy. All right, I'm going to write them vertically. So we have x equals cosine of t, and then y equals sine of t. I'm going to do a legal math move, and I am going to square both sides of these equations. Right? That's legal. All right, so that's going to give us x squared equals cosine squared t, and y squared equals sine squared t. Now we are going to add down. Again, this is a legal math move for us. We've done it when solving systems of equations. And when we add down, we get x squared plus y squared equals cosine squared times plus sine squared. Anytime we see cosine squared plus sine squared, what do we think?
Pythagorean identity.
You got it, Pythagorean identity. This is equal to 1. So this is going to simplify because for it to be in rectangular, there shouldn't be any t's showing. We get x squared plus y squared equals 1. And there's our rectangular equation. Questions at all? So let's talk about the domain a little bit here. So it's telling us that t goes from 0 to 2 pi, and t is the angle that we're plugging into sine and cosine. So basically it's saying one trip around the circle. What we have here, the rectangular we ended up with, what's that the equation of?
A circle.
Could you be more specific?
Well, it's more. Well,
Circle, centered at the origin, radius of 1, unit circle. So I probably would have just pictured the graph of this. And because t went between 0 and 2 pi, it's telling me I want the whole circle. And since it's a unit circle, I know that my domain is going to be from -1 to 1. We could have done it a slightly different way because they gave us t, our definition of t is a sandwich inequality. We could have done it the way that we found the domain for the first one. Could have solved the x equation for t, and if I did that, I would get that t equals cosine inverse of x. So plugging in, that means that cosine inverse is going to be in between 0 and 2 pi. So what we want to think about here is what is the max and min cosine value around the circle, the unit circle. It's tricky. We can't just then take like the cosine of we can't just do that because cosine of 0 and cosine of 2 pi are both the same. But in between 0 and 2 pi, we get a different value. So we're not going to get the correct domain if we just do it this way. So we kind of have to think about it more. So if inverse cosine in between 0 and 2 pi, what is the max and min cosine value? One trip around the circle. And we know that that answer is -1 and +1. That's another way to think about it. But personally, I probably would have just drawn the circle and then said, hey, what's the domain of that circle? Questions, anybody? All right, let's do one more. This one's going to be super similar because we're defined in these trig functions. Just like any of them that have a trig function, you want to solve for the trig function. Could be sine and cosine. It could be secant and cosecant. It could be, you know, any of the 4 trig functions. But usually what we're trying to do is the same thing where we're going to square both sides, add down, and use a Pythagorean identity to end up with 1. Oh, these should all give us conic sections. All right, so let's start by solving for cosine and sine. That's going to give us x minus 2 over 4 equals cosine. And y plus 1 over 3 equals sine. And then we're doing all the same moves. We're going to square both sides. Just be careful here, you got a fraction, so you're going to have to make sure to square the top and square the bottom. It's going to turn this into x minus 2 squared over 16 equals cosine squared. And y plus 1 squared over 9 equals sine squared. We're going to add down. Gives us x minus 2 squared over 16 plus y plus 1 squared over 9 equals cosine squared plus sine squared. Here we have our Pythagorean identity equaling 1. But like I said, these could involve like tangent and secant. So you might end up with that Pythagorean identity to deal with, or cotangent and cosecant. This becomes x minus 2 squared over 16 plus y plus 1 squared over 9 equals 1. Ooh, also, to make the Pythagorean identity work, you might end up with having to subtract, because remember that our other Pythagorean identities are like tangent plus 1 equal, I'm sorry, tangent squared plus 1 equals secant squared. So to get this to be equal to 1, you might end up having to have secant squared minus tangent squared. So just heads up with that. Pay attention to what the trig functions are and how they would have to be combined so that a Pythagorean identity would be applicable. All right, what kind of conic is this? Just to review our conic stuff. What's that look like?
Is that an ellipse?
It's an ellipse. And how do you know it's an ellipse?
There's the plus sign in the middle.
Both variables are squared and we got the plus sign in the middle. So that tells us that this is an ellipse. If I wanted to do the domain, man, this would be horrible trying to do it algebraically, like solving this for t. I don't want to deal with cosine inverse of x minus 2 over 4. So I would definitely graph this. You know, our center's at 2, -1. We're going to go 4 in the x direction. 3 in the y direction. Right, there's our ellipse here. It's the worst drawing ever. But let's go back and look at how they restricted t for us. When they restricted t, they're saying that t is between 0 and pi. So that's only half the unit circle. It's only half of our angles. So it's only going to be half of the ellipse. And I'm going to choose the top half as if I was rotating from 0 to pi. So I would just look at the top half of this ellipse and then be able to state the domain from my picture. Domain's going to be -2 to 6. Questions at all? All right, well, that's all I got today. We'll wrap up parametric equations and then start limits on Friday. So that's exciting. We're starting our first calc chapter, but we'll wrap up parametrics for the first 10 minutes. Anybody questions on anything? You should be working on your chapter 9 take-home quiz and working on getting that submitted. It's probably due on Monday if I were to guess. Well, you know, Sunday night at midnight. I would double check the Dropbox date to be sure on that. All right, well, if nobody has any questions, everybody have a great day. And Garrett, if you want to stay, I'll help you with your calculator.
All right.